Okay, so they can't measure the radius directly because how do you find the edge of a cloud? So they take two atoms, push them together, and measure where the nuclei are at. Half the distance between them is the radius, or I could say the distance between them is the diameter. Ooh. It's not quite because they overlap a little bit. It's not quite how big it would be by itself, but it's a good measure of how big it would be. Okay. So, trends in atomic size. Okay. And they're going to be influenced by those two factors on the bell work today. There's going to be a third one that's going to deal with our exceptions. The third factor is going to deal with our exceptions, but we've already dealt with that, which you'll see. Yeah. One of the things that's going to influence higher energy level. Higher energy level is further away. Higher energy level is better shielded. Another way of saying the same thing. Your book tends to focus on distance. I like to focus on the fact there's electrons in the way. I think that's more a bigger influence, is the fact they got negative charges in there. Negative charges between this negative charge and the nucleus, there's other negative charges which are going to push that out a little bit. Make it less attractive. And charge on the nucleus, more charge pulls the electrons in closer. Because we're using the complicated idea that opposite charges attract. And more opposite attracts more. So just using these ideas, we're going to be able to get the general trends in size, electronegativity, and ionization energy. Hey, you graph this. I did one period at a time, and this is what I got. What can you say the general trend is for atomic size? So every period, it generally decreases. So if you go across, and the cross for us is always left to right, the radius gets smaller. Why? Okay, so we're talking about a row, so it's going to be about nuclear charge because the energy level is going to stay the same. So notice what this is saying, that lithium with 3 electrons is smaller than neon with 10 electrons. No, it's bigger than lithium. You expect the lithium with 3, neon with 10. Neon's got to be bigger. No, look at this graph. Period 1, 1.5 down to about half the size. Right? So, well, you got 3 times as much charge. Should be able to pull it in better because they're all the second energy level. 10 protons is going to pull in. 10 protons is going to pull in that energy level better than 3 protons. To have the same amount of energy on a ladder on the moon, the ladder would have to be 6 times taller because the moon doesn't attract as much. So to have the same amount of energy, the same energy level, I'd be further away. Does it make sense? Less attracted, you got to be further away before you're going to have the same energy. Yeah. Well, it's not so much the hurt, it's the crack in the spacesuit. You see why that you would probably survive better than the spacesuit. So and once it leaks, bad things happen. Okay? So, that extra nuclear charge pulls the electrons closer, so they get smaller. So see how you're going to answer the question about why there's a periodic trend difference, or why neon is smaller than lithium. You're going to answer it differently now than you did on the homework last night. On the homework last night, you could say, because it's further to the right. Okay? Now we got to say, because it's got more protons in the second energy level. It's got a bigger nuclear charge in the second energy level. It's pulling with 10 protons instead of 3 protons. Okay? Okay, so this is lithium. All right? Next electron, where's it going? Out of energy level, right? Because I can fit in the second energy level, I can fit 1, 2, 3, 4, 5, 6, 7, 8. I can fit 8 electrons. So the next electron is going to make it a little smaller. Next electron, same energy level, a little smaller. Next electron, same energy level, a little smaller. And then you get down to neon was much smaller than lithium. And then the next one after lithium, or after neon, I'm adding another energy level. So now when I add another energy level, we can talk about group trends. Hey, you've got this graph, right? I just recreated it using Excel instead of Chrome, or instead of Sheets. So what can you say the group trend is? As you go down periods, it generally increases, right? That's what. So if I ask you which of these is bigger, you don't have to explain what. You don't have to explain why. You can just say, well, they get bigger going down. If I ask you why, then you need to talk about the nucleus and energy levels. Reason why? Every atom going down adds another energy level. So it doesn't make sense to compare sodium with neon. It makes sense to compare sodium with lithium. Seem reasonable? Yeah. So you got another energy level, you got more shielding, you got less attracted electrons. And less attraction means it pulls it in less, which means it gets bigger. Once again, we have an exception right in there, but it is in group, it's in period 4, where we're adding those d orbitals, and those d orbitals are going to add on the inside. They're going to increase the shielding a little bit, right? Because they're 3D, so they're going to increase the shielding a little bit. Not a huge amount, but increase it a little bit. And that's why we get that little exception when we get there. So there's hydrogen, lithium, sodium, potassium. Okay. Now I'm using the Bohr atom. We know it's not exactly right, but it's an easy way to explain the concepts in Schrodinger's model, right? You know it's really S's, P's, and D's, and F's that are sticking out further. Okay. I'm not trying to use an old model. I use the simplest model that can explain it. This does a decent job of explaining it. If I want to do the math, I'd have to go to the real one. Okay, so overall, this is what your graph for atomic radius. Oh, I left one off. I left off helium. So put a hydrogen. Where would helium be? Okay. Okay, helium I can compare to H. So it's got to be smaller than H because it's got more protons pulling in that first energy level. Or I can compare it to neon. And it's got less energy levels, so it's smaller. So either way I look at it, helium's got to be down here. You okay with that? Okay. And then we get a big jump every time we add an energy level. And here's what happens in the D's. This is the part you didn't graph. Okay, so you graphed here and then it went to there. So these 10 in between, a little bit of shielding, or actually more nuclear charge, same shielding, more nuclear charge, same shielding, but all of these are about the same shielding. The extra shielding you put in just about cancels out the extra nuclear charge. Okay? So that's what's going on here. Okay? And those are the trends in atomic radius. Pretty easy to explain. Okay? Because size is pretty easy to picture. That how strongly the electron gets pulled determines how far out it's going to be. More protons pulls it in more. More energy levels pulls it in less. So here they tried to show you by size. They had to stop with these because if you only make 2 or 3 atoms, it's kind of hard to see how big they are. And if they only last for fractions of a second. We can predict, but the math gets pretty ugly when you get that many pieces interacting. It's hard to solve a problem with 3 pieces. Imagine 216.
What's the pattern with that?
They're not exactly sure why that is, but it's about those exceptions and whether they're filling the half-filled or filled orbitals. Okay. So, got a question? Feel free to ask. Which of the following is largest in size? Once you find them on the periodic table, find the first one. The rest are pretty easy to find. I didn't give you a bunch of random ones. Okay. So what trend are we talking about here? It's a group trend. So as you go down, the ionization, the atomic radius gets bigger. Okay? Because it's got more energy levels. Which of these is largest in size? Once you find the third one, you'll realize what the pattern is. Okay, well, where are they at on the table? They're all in the same period, and as we go across the period, nuclear charge pulls it in closer, so it gets smaller, so the largest would be potassium. Explain why. Okay, all right, so why can't it be C and D?
Because
They're in the same energy level. So it's got to be the one with, and more protons would make it smaller. So, everybody see why it's B? Okay. Actually, it's the only one that was true. Yeah. The other three were all false statements, so it's kind of hard for them to be the right answer. They're all right around each other. Check out the zigzag line. I think I've surrounded it. Okay. So you see I've given you a square on the periodic table. Okay. Okay. So which side is going to be larger, left or right? Left. Which is going to be larger, top or bottom? Bottom. So I can tell for sure that the biggest one is going to be gallium. And I can tell for sure that the smallest one is going to be silicon. But I know both aluminum and germanium are bigger than silicon and smaller than gallium. But which one of those is bigger? Okay, because so you got both. So you got extra shielding, but you got extra nuclear charge. The answer is you can't. It's hard to compare that direction. Right? We know they're in the middle, but we don't know what order they're in the middle. You'd have to look it up. Okay, because the question is, does the extra nuclear charge overcome the extra shielding, or does the extra shielding win out over the extra nuclear charge? And usually, well, it's not quite as predictable as you'd like, but usually the shielding wins, and that's why the zigzag line is zigzag. That's showing you shielding winning. Because you stay like a metal longer with all that extra charge in the nucleus. You stay like a metal. Because we haven't really actually said what a chemist means. We've talked about properties like shiny conductors, but we haven't talked about how chemists think about metals yet, because they're worried about how they react. Okay, second trend. Got 4. This is the second one. And just to put it in context, we're looking at early next week for a test. This unit is short because we did all the noble gas stuff already. Right? We did noble gas last one, and that's covered in here, so this unit's going to move fast. Okay? Okay, so ionization energy. If you had to guess off the top of your head, without knowing anything besides the words, what would you guess? The energy to ionize, right? Which, as long as you know what ionizing is, that's okay. And what ionizing is to remove an electron. It's kind of like the photoelectric effect, where you put in energy and it knocks off the electron. The only difference is the photoelectric effect worked on metals, and here we don't actually try to knock the electron off until we've already turned it into a gas. So if it was a solid, we heated it till it melted, then boiled, and then we tried to knock the electron off the gas. Gases rather than metals. So there's already a lot of energy in it before we try to knock the electron off. So if I have an atom with 11 protons and 11 electrons, if I take an electron off, I now have 11 positive pieces and 10 negative pieces. So I have an extra positive piece, so we call that a positive ion. Fact is, we call it a 1 plus ion. Yeah.
Wouldn't that atom be unstable?
No, it's what makes it stable is the nucleus.
Oh,
Okay. So removing it makes a 1 plus ion, and we write charges as 1 plus, so we don't think we're doing math, that we're counting pieces. It has 1 extra positive piece. It's tough for me because when I was in high school, they hadn't changed I learned how to write it as +1. So if you catch me, it's my high school coming back through. Okay, the energy to do that, to take off that first one, is called the first ionization energy. The energy is required called the first ionization energy. That implies that there's a second ionization energy, right? We got to stop and think. There's 2 ways to define second ionization energy. It could be the energy to take off 2 electrons, the first and the second. Or it could be the energy just to take off the second one after you've already taken off the first one. And they decided that it's just to take off the second one. We want to compare how hard the second one is to take off to other second ones taken off. So you see, had to make a decision how they're going to define it. So it's not the energy to take off 2 electrons, it's to take off the second one after you've already taken off the first one. Okay. So when I go to get that second electron, I'm going to take it away from something that already has a positive charge. Is that going to how is that going to affect taking that second electron off? So I'm trying to take it away from not something neutral, something with a positive charge. It's going to be harder to take the second one than the first one. Because instead of taking that electron away from something neutral, I'm now taking it away from something positive. That's going to be harder to do. Okay. What do you think the third ionization energy is? It's to take the third electron off, and it's going to be bigger than the second, etc. How many ionization energies do you have? As many as you have electrons. So we could talk about the 54th ionization energy of cesium. First you knock off the first 53. Then you knock off the 54th, and you still have one left. And the 55th is going to be bigger than the 54th. Yeah, it is possible. You can look up the numbers. Yeah, they do it, yeah. Why? To see how it's a good way of measuring how strongly that electron is attached to the nucleus. Because electrons have to move around if you want to talk about chemistry. So that attraction is going to help us explain chemistry. That's why we're doing all this. This is all about trying to explain how chemicals behave. What? Oh yeah, it's a really big number, yeah. I mean, think about the 92nd ionization energy of uranium. 107. Okay. Okay, and of course the third is going to be bigger than the first and the second, right? Because it's bigger than the second, it's got to be bigger than the first, because the second was bigger than the first. So here's the numbers in different units than you got. I think you got them in electron volts. This is kilojoules. Okay, but there's actually, if you look, there's no second ionization energy for hydrogen. Why? You can't take off a second electron from hydrogen because it only has one. But if you'll notice that if you go across, they always get bigger. But it's not quite here. It's 12,000 times bigger. Here, it's not even twice. So there's something going on here. We want to be able to explain these things too. Okay. And what you'll notice is there's actually a stagger here that I get. There's a where I get bigger. That the pattern is there's a big drop here. There's a big drop here. There's a pattern to where there's a big drop in between the ionization energies. Okay. And if you look at it, where there was a big drop, going across it, there's a big increase. Right? So the places where there's a big drop is the same place where there's a big increase. I've got to try to explain why those are. So first, we're going to look at just, when they say ionization energy, if they don't tell you which one, it's first. Okay? So if they just say ionization energy, it's first ionization energy. If they want any other one besides first, they will put a number in front of it. Well, nuclear charge. The greater the nuclear charge, the greater the ionization energy. Why would more charge on the nucleus give you a bigger ionization energy? Okay, so remember, ionization energy is the energy to pull an electron off. I'm trying to pull a negative charge away from a bigger positive charge. That's going to be harder to do. It's going to take more energy. Reasonable? Increased shielding decreases ionization energy. Because the shields get in the way, so the electron is less attracted. So we're still at nuclear charge more attracted, extra shielding less attracted. It's the same reasons, folks. We're not come up, we got one other piece to add, but for the most part, we're going to talk about these same reasons over and over again. And there's a third one we haven't mentioned for a while. Filled and half-filled orbitals are especially low energy. That means they're low on the ground, and to get them off, you have got to put in more energy. If it's low energy, to get rid of it, you got to get more energy to get away. Always confused me why they launched rockets from sea level. Why not launch them from the top of a mountain? You gain 20,000 feet. And thinner air, so less drag. But carting things to the top of a mountain could be a challenge. And when things go wrong, the rocket usually lands on something if you're on the top of a mountain. Okay. So this right here is where our exceptions are going to happen. Because the first two give us general trends. Looking for exceptions, the reason for the exceptions here are the same reason as the reasons for the exceptions last chapter. So by group, I'm going to do the group ones first, because group is easy to explain. You drew this graph. What is the general trend? It goes down. As you go down, it generally decreases. Only place it's an exception is it's not one you'd expect, one you might expect to be able to predict, but it's those there. And notice that what those are period 4 and 5 where they don't match up. So we're talking about where we added the D's, and it happens just after the D's in group 3 and 4. Does that make sense? So it happens just after those D's. This is group 3 and 4. So the places where you added the D's in between messes up your pattern a little bit.
And that's because we have to make like D4s, like D5.
No, actually, it's because we have to, those D's are building a shield.
Oh, but
Interior, so it's going to make that outside electron just a little bit easier than it should be. So this one drops more than you'd expect it to. Does that make sense?
yeah.
Okay. But why, as you go down a group? What changes as you go down a group? Energy levels and shielding. So more shielding, more energy levels, less attract for that outer electron. Same reasons over and over again. That's what a good theory does. Uses the same reasons over and over again to explain stuff. That's when it gets to be called a theory, when it explains lots of stuff. Hey. Periodic trend. This is what the graph looks like when you. This is the graph looks like if you start over every time. You guys went and connected them back again. I just went back and did one at a time. And what do you get? Well, what is the general trend as you go across the period? Generally increases. Because all the atoms in the same period have the same shielding, but there's increasing nuclear charge. So it's harder to remove the electrons, generally, as you go from left to right across the table. Because if I got bigger nuclear charge, it's going to pull my electron more, make it harder to take off. That's the general trend. Now we've got a couple of little declines to explain. That it happens in 3A and in 6A. Okay, see that's where the two exceptions are, 3A and 6A, where it goes down instead of up. And if you look at the electron configuration, 3A is going to end in S2P1. And what happens if you take an electron away from P1? You're left with S2, which is a full orbital, which is lower energy, which means it's easier to make. It's easy to make something with low energy. It's hard to mess up something with low energy. It's easy to get a bowling ball on the ground. It's hard to get it back off the ground. And group 6A would be S2P4. And if you take one electron away from P4, you're at, take one away from 4? A P3, which is half filled. And half filled is easy to make. So, here's the graph. You guys didn't do hydrogen and helium. Why would helium have a greater ionization energy than hydrogen? It has no shielding, just like hydrogen, but twice the charge. Okay? Okay? So that means it's harder to remove that electron. Okay? Next comes lithium. Does it make sense to compare lithium to helium? No, because they're over there. So what does it make sense to compare lithium to? How about hydrogen? Okay, it's hydrogen. Should the ionization energy be lower or higher for lithium? Should I make it here or here? Okay, so if I go down a group, I'm adding more shields, which means less attracted. So the lithium will be down here. And then, because it's got an extra shield. It has a shield, hydrogen didn't have one. Okay? And notice how the extra shield outweighs the tripling of the nuclear charge. Because I'm comparing one proton to 3 protons. But the shielding won out. It blocked more than, my shield blocked more than two protons. Because that lithium is feeling less than 1 proton. Because it was feeling 1 proton, it'd be right where hydrogen's at. Okay? So next I need to do after lithium comes beryllium. Should it be higher or lower? Higher because same shielding, bigger nuclear charge, right? Okay. After beryllium comes boron. Same shielding, bigger nuclear charge, so of course it is lower. Why would boron be lower than beryllium? By removing that electron, I'm ending up at S2. S2 is full. Okay. After boron comes carbon. Same shielding, bigger nuclear charge. After carbon comes nitrogen. Same shielding, bigger nuclear charge. After nitrogen comes oxygen, same shielding, bigger nuclear charge. It goes lower this time. Okay, but breaks the pattern because I get that half-filled orbital. Okay? There's fluorine, same shielding, bigger nuclear charge. And neon, at neon I can compare to two things now. I can compare it to fluorine. It's got to be higher than fluorine. But I also can compare it to helium. How is it going to compare to helium? Yeah, it's got to be lower, easier to take off because neon has a shield and helium doesn't. So it's higher than fluorine, but lower than helium. And then next comes sodium. Where should sodium be? Lower than lithium. Because I've added an energy level. I've added shielding. So see where we compare? Okay. And then here's the next one. Looks like that. Okay. That big flat line that you drew, this is what's really going on. Okay. Those are your Ds. And this one right here is D5. Half full, hard to break up. Actually, no, it's D6. One more than half full, easy to make. Okay. And then these drop down because we're at, this is D10, so it's down low again. Hard to break up D10. Oh, no, this is D10 here, sorry, D10's up here. Then hard to break it up because it's full. And then easy to break it up, harder, down, up. So it goes up, down, up, down, up, down, up, down, up, down. So you see why we called the ones that had the pattern representative elements? Because the pattern is well represented. It is not represented here. So that's why they're called representative elements, because the patterns work. Yeah.
Why is D9 lower?
It's try to think. Let's do this. This is S1, S2, D1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So D9. It's going to be hard. It should be a little bit because you've got half full orbital if you take the D10 one off. You got S1 D10. No, S1 D9. You still have a half full one. Okay. So we're actually not going to talk about what order they come off. Okay. We're talking about which ones come off. So, which of the following would have the lowest ionization energy? After you get about the third one, you figured out where I'm asking you to compare. Okay, so this is a period trend. TE is right before XE. Okay, so it's a period trend. As I go across the period, ionization energy tends to increase. So the biggest ionization energy, the hardest one to change will be the noble gas. Oh, lowest, that's for lowest. So easy to change is rubidium, sorry. Hardest one to change is noble gases. Noble gases are stable. They don't react with anything. Okay?
The atomic radius is a result of the ionization?
No, atomic radius is a result of the electrons being pulled closer or further away. Ionization energy is the opposite, trying to pull that electron off. So the trends are opposite directions, but because they're caused by the same things. More attraction is going to pull them in more attraction is going to make it harder to take off. Okay, does that make sense? So we're measuring different things. We're talking size versus taking an electron off. Okay, trucks versus tires. Okay, so something with, which of these? Lead. Yeah, because it's the bottom, right? The driving force. Big idea that's going to come back over and over and over again. I think hopefully when I say these things, by now you believe me that's going to come up over and over again. Okay? Full energy levels are very low energy. Full energy levels are dropping the bowling ball into a well. to get it back out of that well, you're going to have to put a lot of energy in to get it back out of that well. Hey, noble gases have full energy levels. So once you look like a noble gas, you're going to be stable. So atoms behave in ways to achieve noble gas electron configuration. They can't be the king, but they can look like the king. They're going to move their electrons around in a way so that they look like noble gases. Because once you look like a noble gas, you're at low energy, and it's going to take a lot to change you.
So does that explain covalent bonding?
It explains all the bonding. All the bonding we're doing. The whole reason why atoms stick together is because they want to look like noble gases. And we're probably going to want to talk about atoms sticking together a little bit if we're going to talk about chemistry. Right? So this idea is going to come up over and over again. How can I make it look like a noble gas? What about second ionization energy? For elements that reach filled or half-filled orbital by removing two electrons, the second ionization energy is lower than expected. So that would be P5 and P2. Right? Because P5 loses the first one, then loses the second one, looks P3. Half full. P5 or P2 loses 2, you're at S2, full.
Wait, can you repeat that?
Okay? So if you're at P2 and you lose 2 electrons, first you lose the first one with the first ionization energy, and you lose the second one, you're going to be full at S2, so it's going to be easy to lose that second electron. Same for P5. It's also true for S2. For S2, it's going to be really low because I'm not just making a full half-full orbital, I'm making a full energy level. So alkaline earth metals always forms 2+ ions. They always react in a way to lose 2 electrons. That's group 2A, if you haven't memorized the parts of the table yet. Oops. And of course, third ionization energy, things that have an electron configuration of S2P1 would have a low third ionization energy. That is group 3A. That is, we don't have a name for that column, so we call it the boron family, because boron's at the head of the family. No, boron was named after the stuff they mine up in boron, which is just up in the high desert. And use it for borax, cleaning stuff. 20 mule team. They in the high desert. They used to pull across the desert with a 20 mule team. So atoms in the boron family tend to form 3+ ions. Okay. A little bit more about ionization energy on Thursday, because tomorrow we've got parts of the table quiz, a lab, and actually we'll probably talk about this tomorrow too. Okay, some homework out of the book. I will see you tomorrow. I will see you tomorrow at the end of the day after lunch. You guys get to end your day with me tomorrow. I get to see you when you're awake. That's going to be different.
You get to see me when I'm tired. This is the only class I'm actually awake.